In our lesson today, we will be focusing on sequences. So for your objectives, students will be able to define sequences both explicitly and recursively. Students will be able to determine limits of infinite sequences, and students will be able to define arithmetic and geometric sequences and use them to solve problems. All right, in our activator, we compared some different types of sequences. And in our instructional focus, we'll take a look at explicit versus recursive sequences. And that's really in how we define a sequence, the ways in which we can kind of write them out or define them. We'll take a look at limits of sequences. And we'll compare arithmetic and geometric sequences. In the activator, the first sequence that we looked at was what we call a finite sequence because it ends at 25. The other three are what we would call infinite sequences because they continue on infinitely. That's what that dot 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 and the 2 to the k or the 1 over k or a sub k, all of those are representing that we're going to have an infinite number of terms in our sequence, and k just represents whichever term we are looking at, or the kth term. All right. In the fourth one, we don't actually have a rule, but we can just use this subscript notation to identify the kth term of a general infinite sequence. All right, so in that sense, an infinite sequence can be thought of as a function that assigns a unique number, a sub k, to each natural number k. All right, so the big difference, though, was the infinite versus finite nature of those sequences. So to start out, we're going to take a look at what we call explicit sequences. And what that means is we're going to define a sequence based on a specific maybe formula where we can just plug in a value for k and it will determine the value for that number in the sequence. So for example, if I said find the first 6 terms and the 100th term of a sequence a sub k, in which a sub k is equal to just k squared minus 1. All right, this is the explicit formula, k squared minus 1. So if I want to know what is the first term, I would just say, well, what is the term when k equals 1? So it would be 1 squared minus 1, which gives me 0. If I want the second term, I would say, well, what is it when k equals 2? It would be 2 squared minus 1, which gives me 3. The third term is just 3 squared minus 1 gives me 8. The fourth term when k is 4 would just be 4 squared minus 1, which gives me 15. When k is 5, it's 5 squared minus 1 gives me 24. And the last one, k equals 6, is just 6 squared minus 1, which gives me 35. If we notice in each of these, we're able to just plug in a value for k and determine the value at that term. If I want to know the 100th term, I could just say, okay, well, what is 100 squared minus 1? And 100 squared is going to be 10,000 minus 1 gives me 9,999. All right, so we're able to find the different terms of the sequence because we have this explicit definition for the sequence or for the function, right? We're able to take a look at the sequence and it's explicitly defined, so it's very easy to just determine any term in the sequence. The next type of sequence we're going to look at is when we have what we call a recursive definition. All right, a recursive definition defines a sequence based on previous terms in a sequence. We have to have an initial term. We have to have this first term in the sequence. So if I tell you that the first term has a value of 3, we've now defined the term. All right, and this one is b sub 1. All right, so it's sequence b. B sub 1 is 3. But then if I want to know for the nth term, right, I would say b sub n is just b sub n minus 1, meaning the previous term plus 2 for all n greater than 1. All right, so it's like if I want to know b sub 2, that's the same thing as b sub 1 plus 2. Well, b sub 1 was 3, so it's going to be 3 plus 2 equals 5. If I want to know what is b sub 3, well, that's just b sub 2 plus 2. So b sub 2 was 5, so it's just 5 plus 2, which gives me 7. B sub 4 is b sub 3 plus 2, right? It's defined based on the previous term. Well, b sub 3 was 7, so it's 7 plus 2, which gives me 9. B sub 5 is just going to be 9 plus 2, gives me 11. B sub 6 is going to be 11 plus 2, which gives me 13. So if we notice, we're adding 2 every time. Now, if I wanted to find the 100th term, well, the 100th term is the 99th term plus 2. Well, the 99th term is the 98th term plus 2. So if I don't have all of those values along the way, it becomes a little bit more difficult to determine the 100th term. If we wanted to, though, we could just say, hey, I understand the pattern. I understand how it works. So the 100th term is going to be 99 terms after the first, and that means 90 times over we're going to be adding 2. So we could just say the initial term plus 99 times 2. So that term is going to be 201. But with an explicit definition, we could have just plugged in the number. All right. In this case, an explicit definition for this function could have been essentially it would be 2 times n plus 1 would be the explicit definition. The recursive definition is when we write it based on the previous terms in the sequence. So that's kind of the difference between an explicit definition where we can just plug in a number and get a value versus recursive where it's saying the next value is based on the previous value. A few other sequences where you may see like a recursive definition would be if you're looking at, for example, the Fibonacci sequence. It's 1, 1, all right, and then every term after that is going to be the sum of the previous term. So 1, 1 goes like this. It goes 1, 1, 2, because 1 plus 1 is 2. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and so on. This sequence would be very difficult to come up with an explicit definition, but the recursive definition is very easy, where we could say, that it's just a sub n is equal to a sub n minus 1 plus a sub n minus 2. This would be the recursive definition if we're given the first two terms are both 1. And this would be for all terms where n is greater than or equal to 3. All right. So it essentially, all right, there are sequences that are much easier to define recursively, and there are others that are not. All right, but we can define sequences either recursively or explicitly, and there are benefits to each way. Now, with functions, we were concerned about end behavior, right? We're also going to be looking at end behavior of sequences. So we can define a limit of a sequence. So if we say let a sub n be a sequence of real numbers, and we consider the limit of a sub n as n approaches infinity, then if the limit is a finite number L, then we would say that the sequence converges, and L is the limit of the sequence. If the limit is infinite or non-existent, we would say that the sequence diverges. So let's take a look then at an example where we need to find the limit of sequences. If I want to determine whether the sequence converges or diverges, right, that's what we want to do. If it converges, then we want to actually give the limit. So if I take a look at the first sequence, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over n. All right, so the explicit definition is that it's just 1 over n. Well, as n approaches infinity, all right, it goes towards 1 over infinity, meaning it is converging. So it converges, and the limit, right, so the limit as n approaches infinity is going to equal it's going to equal 0. All right. So in the first one, it converges and it approaches 0. In the second one, we have 2 over 1, 3 over 2, 4 over 3, 5 over 4. All right. And if we look at this, what is happening in each of these? This is just going to be n plus 1 over n is essentially the explicit definition for b. As n approaches infinity, all right, this is going to converge at a number. It converges again, and the limit as n goes to infinity is going to equal 1, because infinity plus 1 divided by infinity is just 1. All right, for part C, 2, 4, 6, 8, 10. All right, what's happening in each of these is it's just going to be, looks like it's just 2n, right, for our explicit definition. So this is going to have a limit as n approaches infinity of infinity, so it diverges, meaning there is no limit. The next one, negative 1, 1, negative 1, 1, negative 1, 1. So it's just kind of flipping back and forth, negative 1, 1, because it's negative 1 to the n. This one is also diverges because it never approaches a single finite number. It is bouncing back and forth between 1 and negative 1 the entire time. All right. So the first one converges with a limit of 0. Second one converges with a limit of 1. The third one, it diverges because it approaches infinity. And the second one oscillates forever, and so it has no limit. And because it has no limit, we would say that the sequence diverges. Here are a few problems that I would like for you to try on your own. Take a few minutes to determine whether the sequence converges or diverges, and if it converges, give the limit. In order to think about this problem, you may want to think about the degree of the numerator and the degree of the denominator in each of the three problems. Once you think that you've come up with an answer on your own, unpause the video and we'll continue and take a look at the solutions. Okay, welcome back. So we're going to go ahead now and take a look at the solutions. You should have already attempted these problems. And so as we mentioned before, you want to take a look at the degree of the numerator and the denominator. In A, the degree in the numerator and the degree in the denominator is the same. They're the same for each. All right. Because of that, the sequence is going to converge. All right. If they're the same, we know they converge, and we can just think about the coefficient in front of our n. So the coefficients are 3 over 1, so it's going to converge at 3. All right. So the sequence would converge with a limit of 3. In the second one, the degree in the numerator is smaller than the degree in the denominator. When that happens, when we have a larger degree in the denominator than in the numerator, it's going to converge at 0. So the limit as n approaches infinity, and this is how we should be writing this, the limit as n approaches infinity equals 3. The second one, the limit as n approaches infinity is going to equal 0. In the third one, we have a higher degree in the numerator than in the denominator, and therefore this is what we call the limit would be infinite, or the sequence diverges. All right, the limit is infinite, therefore it diverges. So the first two converge and the last one diverges. So now we're going to shift gears a little bit, and we're going to take a look at different types of sequences. There are many kinds of rules by which we can construct these sequences. All right, there are two in particular that we're going to look at because they are seen much more commonly in mathematical applications. All right, so the first of which, we have pairs of successive terms that have what we call a common difference. It's where you're kind of adding by the same amount each time. If we remember in the activator, we had one that went 5, 10, 15, 20, and so on. All right, that particular sequence is one that we would call an arithmetic sequence because we have this common difference. There's a difference of 5 between the first two, a difference of 5 between the next two, difference of 5 consistently throughout the sequence. This is what we call an arithmetic sequence. All right, and those in which pairs of successive terms have a common quotient or ratio, we call a geometric sequence. That would be like having 2, 4, 8, right, where we're multiplying by 2 each time. All right, we have this common ratio between them, or we could divide. The second term divided by the first gives me 2. The third divided by the second gives me 2, etc. We have this common quotient. All right, so in an arithmetic sequence, it can be written in the form of a, comma, a plus d, comma, a plus 2d, dot, 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 all the way to a plus n minus 1 times d, where we're essentially saying that it's some starting value plus the change, the common difference, times the previous term for some constant d. All right, and not the previous term, but the previous number in the term. So like when we thought about the 100th sequence, right, that long one, it was a change of 2 each time, so it was just that initial term, which was, if I recall correctly, it was 3, plus n minus 1 would be 99 times 2, gave me that 201, which tells me how much needed to be added over the course of the entire sequence to get to that value. And that's a way in which we can define an arithmetic sequence. And so this is the formula in a recursive format for all arithmetic sequences. It's a sub n is equal to a sub n minus 1 plus d. That's the recursive formula for any arithmetic sequence, where d is that common difference, and this is valid for all n greater than or equal to 2 because we have to have that previous term already defined. All right, so if we take a look at the example, we want to find, we're going to look at each of the arithmetic sequences, and we want to first find the common difference, then find the 10th term, create a recursive rule for the nth term, and write an explicit rule for the nth term. So we're doing all of those things for each of these problems. Pause your video, take a minute, and see if you can do that. See if you can come up with the common difference, the 10th term, a recursive rule, and an explicit rule for each of those sequences. When you're ready, unpause your video, and we'll take a look at the solutions. Welcome back. So you should have had the chance to go ahead and attempt to find those values for 1 and 2, or the formulas, etc., for the rules for the sequences, as well as the common difference, as well as the 10th term. So let's go ahead and take a look at the solutions. In the first one, the common difference between the terms, we're actually adding 4 each time. It's a plus 4 each time. So that was the common difference. We call that d. All right. If I want to determine the 10th term, all right, if we remember, we take that first term, which was negative 6, and we add that n minus 1, so 10 minus 1, times the common difference. So it's negative 6 plus 9 times 4, which would give us positive 30. All right, so that's where the 30 comes from for the 10th term. When we want to define the sequence, we would say a sub 1 is negative 6, and a sub n is just the previous term plus 4 for all n greater than 2. Remember, when we recursively define a formula or a sequence, we need to start by defining the first term, give it a value, and then define the nth term based on the previous term for all n greater than or equal to 2. The last part, if we want the explicit sequence, we would just say it's negative 6 plus n minus 1 times 4. All right, we can then simplify that to be 4n minus 10 if we use the distributive property and combine like. The second sequence doesn't really look arithmetic at first, but if we think about subtracting the terms, the natural log of 6 minus the natural log of 3 is just the natural log of 6 over 3, or the natural log of 2 by the law of logarithms. And the difference between successive terms continues to be that natural log of 2. So it does, in fact, have this common difference of the natural log of 2. Then, using the exact same rules that we looked at before, we're able to come up with answers to the other pieces. The 10th term is just going to be the natural log of 1536. When we go ahead and say it's the natural log of 3 plus 9 times the natural log of 2, using the rules of exponents, we're able to come up with that. And we can define the sequence by just defining the first term. A sub 1 is natural log of 3, so a sub n is just a sub n minus 1 plus the natural log of 2 for all n greater than 2. And the explicit definition is the natural log of 3 plus n minus 1 times the natural log of 2, which, if we want to simplify that and work that all out, we can move the coefficient in front of the natural log of 2 and change it to the exponent, and we end up getting the natural log of 3 times 2 to the n minus 1. And that all works out as an arithmetic sequence. This is actually pretty tricky given the nature of natural logs, but if you're good with your rules with logarithms, that shouldn't be too problematic. The other type of sequences that come up frequently in mathematics are geometric sequences. And a sequence a sub n is geometric if it can be written in the form of a times r squared, all the way to a times r to the n minus 1 for some non-zero constant r. There's some number being raised to an exponent. All right, that r is called the common ratio. Each term in a geometric sequence can be obtained recursively from its preceding term by just multiplying times r. So a sub n is a sub n minus 1 times r for all n greater than or equal to 2. So for the two problems we have here, we're going to do the same thing. We're going to find the common ratio, the 10th term, a recursive rule, and an explicit rule for each. Pause your video, see if you can work through those problems, and then we'll look at the solution. Okay, welcome back. You should have had a chance to go ahead and try and find the common ratio, the 10th term, the recursive rule, and the explicit rule for those two sequences. So let's take a look. So in the first one, the ratio between them is we're just multiplying times 2 each time. So r would just be 2. All right. To find the 10th term, we would take the first term, which is 3, and we would multiply it times that ratio 2 raised to the 10 minus 1, or 2 to the 9th. In doing so, we do 3 times 2 to the 9th, and it gives us 1,536. The recursive definition is simply taking that first term, a sub 1 is equal to 3, and then saying a sub n is just 2 times a sub n minus 1 for all n greater than or equal to 2. The explicit definition we see right here, right, when we try to find a sub 10, it's just going to be 3 times 2 to the n minus 1. For the second one, we can apply the laws of exponents to kind of work out the ratio when we do the division. We take the second term divided by the first term, and it's 10 to the negative 1 over 10 to the negative 3, which gives us a ratio of 10 squared, which we could also say the ratio is 100. All right. To then go ahead and find a sub 10, what we would do is we would just say that it's the first term, 10 to the negative 3, times that ratio, 10 squared, raised to the 10 minus 1, which gives us, when we simplify, 10 to the 15th. The sequence we can define recursively by just saying the first term is 10 to the negative 3, and the nth term is just 10 squared, which was the ratio, right? The ratio times the previous term. So a sub n is going to equal 10 squared, which is r, times a sub n minus 1, which was the previous term for all n greater than or equal to 2. And the explicit definition we get once again right here from the a sub 10. It's just that first term, 10 to the negative 3, times 10 squared raised to the n minus 1. We can then simplify our exponents, and we end up getting 10 to the 2n. So in this lesson, we learned about infinite sequences and ways in which we can define them. We were able to express sequences both explicitly and recursively, and learned how to express the limits of converging sequences. Lastly, we defined arithmetic and geometric sequences and learned how to apply them. You should be able to define a sequence explicitly, define a sequence recursively, find the limit of an infinite sequence, and use arithmetic sequences and geometric sequences to solve problems. We didn't get too much into the detailed problems with them, but we at least learned how we can use them, how we can define them, and hopefully as we take a look at some problems where they can be applied, you're going to be able to do that as well.